well, we're going to get out of my Discord. So while we're waiting, I'm going to ask you guys to sign the attendance and download the files that we need for today's workshop. So this is the attendance link up here. It should be in the chat. And these are two links. They've been dropped in the chat already. These are for the files that you're going to need for this workshop. The first one is RE-Win. That's for Windows and Linux machines. And the second one is RE-Mac. That is if you're on a Mac. I made it so you should be able to run these files. You might not be able to, though. These are compiled binaries, and they're definitely not going to work for some people. But these are zip files. You can go and download them. Set them up in Kali or whatever environment you're planning on using so that we can get those ready to use. I'm also going to bring you guys down a little bit. There we go. Yes, the files are case sensitive and the text here is not. If you check out the chat, you should be able to see the links. RE and then _ W and then lowercase IN. So I'm going to assume that everyone's doing all right and they've got that. Because if you fall behind on this one, you might have a hard time catching up. So again, remember to sign the attendance. You need to attend at least half of the workshops to qualify for full club membership. That lets you vote in the AGM, be part of the club, have a say in how it's going to be run. Yeah, no more 329 questions on the attendance form. The 329 bonus participation marks that you got was actually only for the first meeting that we had. It just accidentally got left on the attendance form. If you thought you were getting participation by coming to all of these workshops, you were not. That was only for the first one. So yeah, we're going to give it one more minute. I'm going to let people download these. Reminder that you should also have already downloaded Cutter, which is a program that we're going to be using in this workshop. If you don't have that, you should go get it. So yeah, that was the question. Are we getting attendance for this? We're not for 329 anymore. You're just doing this because you like it. Yeah, you're just still here for the info. Okay. I'm going to say let's keep going. So, reverse engineering. We're starting to get into, I'm not going to lie to you, we front-loaded the sort of lighter fun stuff in our schedule this year. So the things that we're going to be doing now are the things that you might think of as the more hacker stuff. If you saw this on a movie or a TV show, you'd be like, oh yeah, that person's definitely hacking something. It's going to be a little bit overwhelming, and it's meant to be. This is supposed to be really difficult, and I'm going to show you a bunch of stuff today. It's barely going to scratch the surface of what reverse engineering is, but it's going to be a good intro just to get your feet wet so that you understand what it is that you're trying to do overall when you're trying to reverse engineer. So the goals of this workshop are to learn what reverse engineering is, to learn some basic tools for reverse engineering, to see what basic disassembled code looks like, and to try some reverse engineering problems. So by the end of this, you should know the answers to questions like, what is reverse engineering? What do I do to start reverse engineering problems? What am I trying to do? What am I looking for? Some helpful courses for this topic are Computer Science 355. That's computing machinery. That's going to be the course where you do assembly code. That's going to be where you learn assembly, and we learn ARM assembly in 355 at the University of Calgary. So if you've done this course, you have an advantage at learning this right now, that you might find this a little bit easier, but I warn you, we are not using ARM assembly. We are going to be using Intel assembly. It's a whole different assembly language. But it should be very familiar to you. For people who haven't taken this course yet, who might be in first year, that's okay too. This is going to be a little bit overwhelming because you're going to look at a new language, but I'm going to step you through some of the basics of it, and you're going to start reading it and trying to figure out what it does. So 355, a very important course for doing things like reverse engineering, and the next workshop I'm teaching binary exploitation. Another useful course, computer science 525. You do a little bit of reverse engineering in that course when you're trying to break files. And computer science 527, the computer viruses and malware course. This course was where they did a lot of reverse engineering to figure out what malware did. Fourth year was when you would take that course. The problem, of course, is this course no longer exists. Dr. Aycock, who taught it, decided that he didn't want to teach it anymore, and so it just doesn't exist anymore at the U of C. Unfortunate. I'll never forgive them for it. Tools that we're going to be using are GDB. So GDB is a debugging tool that works on the command line. So you might have used Visual Studio Code, and it has debug tools. If you've done Computer Science 233, then you've used Java, and you've probably used Eclipse or IntelliJ, and those have debuggers built into them where you can just run your code line by line and see how it's working. We're going to use GDB, which is all command line based. You're going to learn the basics of GDB. You're then going to learn to hate GDB, and then you're going to really learn it at some point, and you're going to love GDB. The other tool we're going to use is Cutter. We'll do a demo, we'll use it, we'll look around in it. Cutter is a program for reversing binaries to see what they're doing. It's a pretty straightforward version. I'll talk more about other reverse engineering programs that are out there. Cutter is the first one that I think we used when we started the club, so it's the one that I know best, but we'll talk about that some more later. But you should have downloaded Cutter already, and you should have GDB installed. So the first thing I want you to do is change the permissions for the files that you've downloaded. So the files that you've downloaded are likely not executable right now. What you need to use is chmod 0777 and then the file name to give yourself permission to run those files. So you're going to want to unzip them, put them somewhere, and run them. And I'm going to go into Kali. I'm going to show you I've unzipped the files. Here they are, and I've put them in a folder. So here's reverse 0, reverse 1, reverse 2, reverse challenge, and the lol code file. If I go in here in the command line and see what's going on, as you can see, I can read these, but I can't execute them. Is that right? Yes, I don't think I should be able to run these yet. Yeah, so it gives me permission denied when I try to run them. So what I want to do is chmod 0777 to change the permissions on that file, and then I'll do it on reverse 0. So now when I check the permissions on reverse 0, there it is. You can see it's different than it was before. These ones just allow read. This one's going to allow read, write, and execute for everyone. We've opened it wide up simply to make sure that it works. Yes, the other way to do this, not in the command line, is you can go in here and click on the file. So reverse 1, properties, permissions, and then allow this file to run as a program. You can do it that way, but let's just admit that it's nowhere near as cool as using the command line. Also, it's really good to learn how to use the command line to do these things. So now when I run reverse 0, it works. It doesn't give me permission denied. So make sure you do that for reverse 0, reverse 1, and reverse 2. So I'll go ahead and do that right now. Reverse 1 and reverse 2. Remember, you can just hit the up arrow to bring up your last command and just change the thing at the end. And now I should have, yeah, all of my files are now executable and readable and writable by everyone. Anyone that's in 329, this should be familiar. We spent a tutorial looking at this stuff. Okay, so we've got our programs ready to go now. This is important because later on we're going to be running these, and if they give you permission denied, it's going to be because you forgot to make them executable. So this picture is very important for what we're going to do today. This is a picture of what happens when we compile a C file. And for this workshop, reverse engineering, and for the binary exploitation workshop that we're doing in, I think, 4 weeks possibly, we're going to be using C. Now, a lot of you probably haven't seen C, and that's okay. We're not going to be using some complicated C. You probably won't see C files until computer science maybe 359, the second assembly course. That's when you start using C, and then in third year you start using it a lot more. There's no course that's really going to teach you how to use C. You're just going to be expected to understand it. If you've done Java, it's similar. It kind of reads similar. But what I want to show you here is when you use a C file, you need to compile it in order to run it. Anyone who's done the Java course in first year, if you're in first year right now, you're just doing Python. Python, you don't need to compile. When you run a Python file, it just runs. A lot of other languages, if you want to actually run the file that you've written, the code that you've written, you need to do something called compiling it. And what that's doing is translating it from the computer code that you've written, so in this case C, and it's translating it down into this, the executable file. This is called the binary file because it's literally in binary. This is just ones and zeros. This is the file that the computer can read, because remember, the computer speaks zeros and ones. The computer does not speak C, it doesn't speak Python, it doesn't speak Java. It doesn't know what those languages are. It takes them and it turns them into zeros and ones and then uses those to run through the machine. So compiling is this process. So it takes your source file, the thing that you've written in human language. This is called a high-level language because it's closer to English. Humans write things in high-level languages because we work in English, and that's a higher-level language. It then gets passed here to the compiler. The compiler then translates it into a second language, assembly. Remember that Computer Science 355 course that I mentioned? If you haven't taken it, the compiler is translating C files into assembly code first, and then it takes it and passes it to the assembler, which links it up with a bunch of stuff and turns it into the executable file. So the important thing to understand here is that the code that you write gets changed by a compiler into assembly, and then changed from assembly into zeros and ones. And what we're going to be doing, the process of reverse engineering, is going backwards through this process. So if I gave you a file that was written in C and asked you what it did, you could probably read it and figure out pretty quickly what it's doing because you know how to read programming languages. And it would look very familiar to you. But if I gave you a bunch of zeros and ones, you can't read that. That's the machine language. That's the lowest level language there is. So what we want to do is we want to translate it from the zeros and ones, hopefully back into C, something that's really easy to read. The problem is that this is not an exact science of getting it back into the C file. The best way I've heard it described is that trying to get an executable file, a binary, back into its original high-level language is a lot like trying to turn hamburger back into a cow. It's gone through a really complicated process. It's been transformed a bunch of times. You can't just undo it. The trick here, though, is that we can get it back into something that's somewhat close to C. And we're going to learn today why it is that that's not exact and why it's close. Another trick to it is that we can get it to assembly code pretty accurately. We can turn the binary into assembly pretty accurately. We can't turn the assembly back into C with a ton of accuracy, depending on the way that it was compiled. And we're going to see how the compiler works a little bit. So yes, your takeaway here is that you take the source file, you turn it into assembly, and then you turn that into the executable. Reverse engineering is all about taking this binary file and try to figure out what it does by reversing this process and reversing these steps to see what you can figure out. So the basics of a C program look like this. If you've never seen a C program before, this is the Hello World program written in C. Up here, you have the libraries that you're importing. If you've used Python in first year, these are your import statements. So these look familiar. This is a little different. So Python can use a main function. It doesn't have to. Java does use a main function, and C always starts at a main function as well. So I'm going to tell you that you want to check out main to start out with, and it's because your program is always going to start in the main function. It should always start in the main function. I'm not 100% if it always does. It should. I don't think I've ever seen one that didn't. This program starts at main, so it goes into this function called main. It runs this print statement, printf, for hello world, and then it does return 0. Return 0 is something that you'll learn about later on. You don't need to worry about this too much right now. But this is just the main structure, the basic structure of a C program. It starts in the main function. So we have a binary file called reverse 0. I haven't given you guys the C code for these files, so you can't open up the source code and see what it's doing. All you can do is look at the binary, and you can try running the binary. You can try doing a lot of things to it. So let's take a look at our first binary. Our first binary is called reverse 0. You've seen me run it. So the first thing you can do with a binary is you can run it. Let's go back, clear my screen. Let me just check. Is this big enough? Like, can you guys see what's on my screen right now? I'm not seeing much. There's a long delay between what I'm saying and the response that I get from you guys. Also, I'm not in that window anymore. Sorry, this right here. Are you guys able to read this all right? This is big enough? Okay. So yeah, we're in the folder where we have our programs. To run a binary file, you do dot slash and then the program name. So we'll run reverse 0. So we can run reverse 0. What is it doing? It seems to print out 5. Okay, what happens if we run reverse 0 again? It prints out 5, it prints out 5, it prints out 5, it prints out 5. This program seems to print out 5. My question to you is why? What's it doing that it's printing out 5? We want to figure out what this program's up to. You don't have the source code, so you can't just open up and read the C file. So we need to figure out what it is that this binary is doing. So what's some other stuff that we can do? What's some other stuff that we can do with this binary? Well, we can run strings on it. If you guys remember the first workshop we did on Linux basics, we learned about strings. So strings is a function, is a program in Linux that we can run on a file, and it'll look through it to see if it can find stuff that looks like English. So this is compiled, but there is still stuff in there that is English, or that's ASCII characters. So remember, strings goes through and tries to find at least 4 characters, and it prints anything out that's at least 4 ASCII characters long. So we can look through here, and there's a bunch of stuff that we can read. This all makes some sense to us. Some of it doesn't make a lot of sense at all, though. Like, what is this stuff? That certainly isn't English. It's a bunch of characters, though. Here's something. Ubuntu. That's interesting. Something about registers. There's a global thing here. Frame. Something about dynamic. Global offset table. It's being shouted at us because it's all in caps. So there's a bunch of stuff. This doesn't make any sense to us, though. The problem is that this is not telling us why the program is printing out 5. I'll go into a little bit about what all of this is afterwards. So strings isn't giving us an answer. It's just looking in there and seeing if there's anything that's in English, and nothing in English is explaining to us why it's printing out 5. Okay, what can we try next? XXD. So this is something that I've demoed in 329. I think we might have used it in one of our workshops. XXD is a hex dump. So I run XXD on reverse 0, and this is what I get. This is a lot of stuff. This doesn't necessarily look very helpful to us. But we can see on the right side here, here's some of the stuff that we saw earlier. Dynamic, frame, global offset table being shouted at us. What is it we're looking at here? What we're looking at is the entire program. This is, remember I said the program is a binary, it's all in ones and zeros. XXD is translating those ones and zeros into hex. Here's the top of the program. Into hex, these are hex bytes. And then this side over here is translating those hex bytes, these things, into ASCII. So it's saying if this was an ASCII character, this is what it would look like over here. You can see there's no ASCII characters over here because these things don't translate. We've got an X right here because this first thing, this translates into an X. If it was ASCII, it might not be. What you're looking at is these are the these are the lines in the program. So the addresses of each byte that's in here. These are all the bytes, the zeros and ones translated into hex, and then this over here is what those hex bytes would look like if they were translated into ASCII. So we can look through here and we can see some English stuff. There's Linux, GNU. Nothing in here is telling us about why this program is printing out 5, though. It's still just a bunch of that stuff that we saw in strings. And what strings was doing, actually, was it was looking through these bytes as well in the same way, translating things into ASCII and then saying if there was at least 4 on this side, like if these things over here, if we see at least 4, then strings would print it out for us. There are clues in here about what's going on with this file. When we see that like hackers attack and we see people analyzing the attack, one of the things that they can do is they can look at the binaries that might have been left behind and see this kind of stuff that's in here. What this is telling us is that the person that compiled this was using Ubuntu. That person was me, and that's what I was using. So it's something left behind telling us about the compiler, GCC. Yeah, but that's not telling us why the program's printing out 5. So interesting, but not helpful right now. We can use Vim, everyone's favorite Vim. So let's try running Vim on this. And if anyone remembers what happens here, you're in for a treat. If I can write clear, that'll help as well. Reverse 0. So let's Vim reverse 0. Oh, brilliant, brilliant. This is great. This is really helpful. Okay, what are we looking at right now? Well, Vim is a text editor. What Vim is doing is Vim is reading everything in that file the same way that XXD was showing us everything that was in there. Vim is taking it and trying to translate it all into text. And Vim doesn't know what these are. These are not ASCII characters. So it's just printing out some stuff here to show us there's something here. It doesn't translate very well, but we can see that some of that stuff we saw before is in there. So Vim is able to read some of the stuff in there as ASCII as well. And this is the program, but there's nothing in Vim that's telling us what this is. Whenever you open something in Vim and it looks like this, it's telling you that this is probably a binary. This is, if it looks like this, it's very likely a binary. In our forensics workshop, we talked about magic bytes. Somewhere at the beginning of this file, there is, let me just get out of it. Sorry, when you get out of this, go Q exclamation point, sorry, semicolon or colon Q exclamation point. Don't write anything in this file. Remember, this is the ones and the zeros that run the program. If you change these, you can destroy the program pretty easily. And we don't want to do that. So I'm going to go Q exclamation, which force quits. It does not save. So yeah, Vim's not what we want. We can use GDB. So we're going to try out GDB. So the way we use GDB is we type GDB and then reverse 0. and GDB loads up. This is our debugger. This is what it looks like in all of its glory. Super fancy. So how is this going to help us? What's GDB going to do? If you've never used this before, it's not obvious. All you've got is your command line here. What does it want you to do? Well, we could run the program. It says that it's starting the program. It's located here. It prints out 5, and it says the process exited normally. Doesn't tell us anything. Doesn't tell us why 5 is being printed out. But we're going to come back to GDB. It's going to be very helpful later on. We can ask GDB what's going on inside the file, though. Let's ask it to disassemble main. So we're going to ask GDB what's happening at the main function in this file. And since we know that C programs start at main, you can usually start by disassembling main and checking out what's happening at the start of a program. So let's go ahead and do that. Ah, interesting. This is new. We haven't seen anything like this before. What is this? What is this telling us? This looks insane. This isn't C. I can't read this. There's numbers in here. I could make them add up to 5 somehow, but that's not really helping us. Yeah, someone said we can see print F in here, and you certainly can. Oops, sorry about that. You can see print F in here, so that's good. The program is printing a 5, so maybe that's where it's coming in. Maybe the program's printing down here. Yeah, this isn't good right now. We're going to get out of this. So let's quit. We're going to see what that is soon. So GDB will show us something, but we're not quite clear on what it is. Now we're going to open reverse 0 in Cutter. So we're going to go back to Kali. If you have Cutter downloaded, you should have it. It should be an app image file. It also likely won't be able to run unless you give it permission. So if you right click on it, go to permissions and allow this file to run as a program, you will be able to start it. This is what you see when you start up Cutter. So first thing, it's asking us to set up some settings. What I want you to do is I want you to go down and go to either dark or midnight theme. It's much easier on the eyes. If you're one of those terrible people that uses light mode in your programs, I don't know how you get through the day. You're going to burn holes in your retinas. So we're going to go to midnight theme, dark mode. We get this screen now. It's asking us what file we want to open. I'm going to select a file. It's on my desktop. Nope, it's on my desktop. Documents, reverse engineering. We want reverse 0. I'm going to open it. Then I'm going to select open. It asks me to change some settings if I want to. We're going to use the defaults that are set here. And we're going to click OK. It analyzes the file, and then it runs. So you're now looking at the dashboard in Cutter. There's a whole bunch of stuff here. This might not look familiar. Nothing here seems to be telling us why 5 is being printed. What you're looking at, this is a whole bunch of information about the program. It's analyzing it and spitting out some information for you. We don't need to look at this right now. Down on the bottom, there are a bunch of tabs. We're going to move along these tabs. So the first one is the dashboard. Second one is strings. Remember when we ran strings in our command line? Cutter will do that for us as well. So I click on this tab, strings, and it'll show us all of the strings that it's finding inside the file. I can scroll down, and we saw all of these earlier. So Cutter nicely has a built-in feature that will look through the binary and find all the strings for us. Over here on the side, it's telling us where that string is in the file. And then it's telling us some information about it on the right side. Fahim says, my Cutter isn't working. I'm not sure what the problem is exactly, Fahim. You need to give us a little more information about what it is that's not working. Maybe try the Discord, sending a message in there. Someone might be able to help you there. you got to make sure that you set it to you gave it permissions to run. Sorry. You had to right click, go down to properties, permissions, and allow this to run as a program. So yes, we're looking at strings here. I'm going to try to slow down a little bit to give you guys some time to actually look at this on your own computers, in case you're just following along here, if you want to try it yourself. So yeah, strings, that's useful. Imports. This is giving us a list. There's some stuff in this list. It looks, again, like some of that gobbledygook we saw earlier. Oh, interesting. Printf is here. This is importing printf. So those import statements at the top of the C file, the include lines, those are libraries that it has to bring in, and this program is bringing in printf. So it's very likely using printf, and it's telling us here that it's a function that it's importing. You have a search feature on the next tab. This will let us search through for specific things inside this file. Nothing in here yet. We don't know what we want to search for. Next, we're going to go to disassembly. And this is where things start to get interesting. Remember when we disassembled main in GDB, and we got some stuff that we didn't really recognize? Some of you might have recognized it as assembly code. Cutter will also disassemble the program for us. And this is one of the main things that this program can do for us, is it can reverse the program, reverse the binary, and turn it back into assembly. Which we can try to read. So disassembly is interesting, and there's lots of stuff. You can scroll up and down. There's all kinds of things happening here. What are we looking for, though? On the left side, there's a list of functions inside the file. You'll see it up here. It says functions, and then there's a list down the side. You'll notice that one of them is main. Remember, our program always starts at main. It's considered a function inside the program. Further down, you'll see sim.imp.printf. So that's the printf function in the program, but we want to go to main. Let's double click on main, and it brings us there. On mine, it's down here. I'm going to scroll a little bit. So this is the main function in this binary file. It starts right here. You'll see int main. And then this thing here is where it imports arguments. If you're familiar with that from Java programs, maybe from C programs. Then there are some more lines. These first lines here are declaring variables in the program. So like in your programs, if you want to say, I have an int, it is called Jeremy, it is equal to 3. That's the kind of thing that is being set up here. It's showing us that there are variables being declared in this program. Right here is where it's telling you the name of these variables. And then these are the assembly instructions that are running the program. These might not be very familiar, though, but that's okay. We're going to take a look at what some of these instructions do. Yeah, int Jeremy equals 3. If you take away anything from this workshop, it's that int Jeremy equals 3. Okay, so we've looked into Cutter. There's some stuff in there. I've told you that it's assembly. It's telling you what the program is doing. But if you're not familiar with assembly, then you might not know how to read this stuff. So let's go in and see some of the basics of how assembly works. What you need to know about assembly is that there are instructions. Each instruction, each line in assembly is an instruction, and it does something. What it does is it moves things, it adds things, it subtracts things, and it moves things between registers and memory. So your computer has a bunch of memory spaces that are reserved for assembly to use to move things around and keep things for itself. They come in different sizes. So up here, it's telling you about the sizes of these registers. They have different names. So RAX, RCX, RSI, RBP. Down here, some of them are numbered R12. What are these? Well, we can go online and we can see it'll explain what some of them are. Some of them are reserved to do very specific things. Some of them keep track of very specific values for the program. Some of them are just free to store whatever values the program wants it to. What you need to, the way I like to think of it is registers are like little boxes that the program has, and the program can take something and put it in the box and leave it there until it needs it again. These boxes come in different sizes. You can see there's an 8-byte register, 0 to 3, 0 to 1, and 0. We know that a byte is 8 bits, and so 8 bytes, each byte is 8 bits. 8 times 8 is 64, meaning that these registers, these names, these are 64 bits, zeros and ones. So 64 zeros and ones can be held in each of these registers. When we say that a program or a computer is, a program is 64-bit or 32-bit, when you go to download it, it asks you if you want a 64 or 32-bit version. This is one of the things that it's referring to, is the size of the memory addresses that the program can read. This one over here is for half the size. So instead of 8, these will usually be 4-byte registers. So 4 times 8, 32. These will be 32 bits. 32 ones and zeros. This will be half of that. This will be 16, and these will be 8. Sorry, the question was, is this 8086? Yes, I believe so, or it's based on 8086, at least. This is Intel x86 ARM assembly. This says x64. I've taken it off a cheat sheet from a slightly different version, but this is Intel assembly. In 355, we use registers for ARM assembly. You might remember them as X and W. X means 64-bit, W means 32, or maybe it's 32 and 16. I can't remember. It's been a while now. And then you use X0 through X31, I think. That's what these are. So just remember that these are pieces of memory that assembly will use to remember specific things, and they come in different sizes. So now we're going to move on to some of the instructions. There's a cheat sheet that we're going to drop into the comments. You can look at a whole list of what the instructions are. I'm only going to show you a few of them right now. So we're going to look at move, add, and subtract. These are the 3 that we can use to figure out what this program is doing. So what does move do? Move will move values from the source to the destination. That might seem a little confusing. So here's an example over here. This is a line. It's an instruction in assembly. It says move 10 into EAX. Remember that EAX is a register, a place that it's going to store a value. So this move instruction is moving the value 10 into EAX. So yeah, it copies the source, the second value, into the first value. That's what a move does. Next thing is the add instruction. Add will add the destination and the source together and store them in the destination. So add DST SRC, these 2 values, is the equivalent of DEST equals DEST plus SRC right here. So it takes these 2, adds them together, and stores them in the first one. So right here, add 10 to ESI. It adds whatever is in ESI with 10 and puts it all back into ESI. Same thing with subtract, except it's with subtraction. And this looks a little bit different. You can subtract EBX from EAX and store it back in EAX. So you can use immediates, these whole integer values like 10, or you can use another register. You can say, take whatever the value is in that register, subtract it from whatever's in here, and store it back into here. So now that we've looked at that, here is a little, this is what, 5 lines of assembly. I'm going to give you 2 minutes. See if you can tell me what the values in EAX, ECX, and EBX are at the end of this. So there's 3 registers being used. It's moving, adding, and subtracting some values. Tell me what is in each of these 3 registers at the end of this program. 2 minutes on the clock. All right, answers are rolling in. I said 2 minutes on the clock. I kind of lied. Answers we got were EAX is 6, EBX is 4, ECX is 6, and that's correct. So for anyone that isn't finished yet, I'm going to trace it quickly for us. So we have a register EAX, we move 4 into it. So we move 4 into the EAX register. We move 6 into the ECX register, so that's added there. We then add them together. So remember, this add instruction is going to add ECX and EAX and store it in EAX. So these two values are going to get added and stored here, so that 4 then becomes a 10. We then move 4 into a third register, EBX, and then we subtract EBX from EAX and store it in EAX. So this EAX is going to have whatever's in EBX subtracted and stored here. Bam, we get 6. So the answer is 6 and 6 and 4. Nice. You guys are awesome reversers already. So now that we know that, you can go back to the reverse 0 program and you can figure out why it's printing out 5. I'll just go over some of these things. These things up here are declarations, variable declarations. The names are right here, var_ch, var_8h, and var_4h. You'll see them show up. It's moving things into them. It's moving things around. I'm going to warn you that the first 3 lines of this program you shouldn't care about. What that's doing is it's setting things up for the program to run. Anyone that's done assembly, that's done 355 will remember that the first lines that you run in your program are almost always the same. That's what these are in this program. You're trying to figure out, remember, why this program is printing out 5. What's going on inside? Remember that this is going to be some C code that was translated into assembly. So you're going to look at this and then try to imagine what the original C code looked like. It's not complicated. I'm going to give you guys, let's say, 2 minutes to look through and see if you can figure out why 5 is being printed out. One more minute. Yeah, Dr. Manzaro would be thrilled. All right, anyone got it? Anyone know why 5 is being printed out? What's going on? at least someone should, because I think they did this workshop last year. Yeah. Yep. Renekton got it. 2 and 3 are being added together and then printed. It's not a complicated program. What you're seeing here is that it's moving 2 and 3 into these variables. It's not using registers. It's using those variables, var_ch and var_8h. Remember, it declares them at the top. It moves them into 2 into that and 3 into that. It then moves it from there into registers. So from var_ch into edx and in the eax, it then adds those two registers together. So it adds edx and eax, stores it in eax, and then moves eax into var4. Then it moves var4 back into eax, which makes no sense to us because it just moved it out of there. Then it moves eax into another register called esi, and then does something here. This is a load instruction. We didn't go over this. You don't really need to know this. It moves 0 into eax, and then this is a call statement. So it's calling another function, and it's calling printf. So this is where it's running the print statement. That's all this program does. We're going to see this is the program. This is what you were just looking at in assembly. These are the import statements, the start at main. Remember those 3 variables that assembly was declaring? They were 3 integers. They were answer, a, and b. A is equal to 2, b is equal to 3. It then adds them together, stores them back in answer, and then prints out the answer. So again, if we look back, there's the 3 variables that are being declared. It'll tell us that they're ints, so those are integers. var_ch is going to be a because it gets 2. var_8h is going to be b because it gets 3. And you're going to notice that var_4h is the answer, so that's where it's moving the result into, and then it prints it out. So that's it. A very simple program. You might think I've never seen C before, but that's all it looks like. It should be pretty familiar to you. Yeah, congratulations. You've just reversed your first program. So we're going to get a little more complicated now. We're going to go into conditionals and jumps. So in programming, when we want to jump, we usually will write something like an if statement. If this, do this, else do that. In assembly, we have something kind of similar. It's called a jump, and it's based on a condition. So here are the things. There's basically 2 things you need to know, a compare and a jump. So the compare is going to compare 2 values. In this case, it's going to be B and A. After this, there's then going to be a jump statement. And the jump statement is going to depend on what the comparison did. So compare is just going to compare 2 values. Underneath the hood, it's setting a bunch of flags, a bunch of bit values. And then these are jump statements. These are all different. Any one of these could follow the compare. These are going to check those flags and decide what to do. So we compare A and B. JE says jump to label, this thing here, label. Jump to label if B is equal to A. So JE is jump if equal. So if B and A were equal and we hit this line, it would jump to whatever the label is, and I'll show you what that is after, if A and B are equal. Jump if not equal, so if B and A aren't equal in the compare, then it'll jump to label. If B is greater than A, then it'll jump to label. If B is greater than or equal to, less than or equal. Test is similar to compare. For our purposes, let's just imagine that it does the same thing. It doesn't, it's slightly different. But yeah, these are what the jump labels do. We're going to see what that does here. So let's imagine that we have a value called input. This is more like pseudocode, partially pseudocode. Let's have something called input. Let's say that the value of input is the letter B. So our first line is going to compare input, which we know is the letter B, to A. And then it says jump if not equal to L1. That's the label. It's going to be down the side here. A and B are not equal, so this is true. So we're going to jump to L1. So we skip these 2 lines of code and we go down here. We then compare input and B. Let's pretend that our input is a capital B. Let's say that these are the same. So these are compared. They are equal. So jump if not equal to L2. They are equal, though. If they were not equal, this would be true, and we would go down. This is not true because the values are equal. This is a bunch of logic. This is why we take logic in first year. The values are the same, so we don't execute this line, or this line doesn't do the jump. Instead, it keeps going. So we then say some code runs. There would be some code in here. So the code would run, and then it says jump to L3. This JMP is just a jump. This says no matter what, jump to L3. And this is what if statements look like in assembly. It does a compare, and then it does a test and figures out if it's going to jump somewhere. So this is going to be like an if-else sort of thing. So now that we understand how compare and jump works, I wasn't supposed to do that. Take a look at reverse 1 in Cutter. So we're going to go to, where's my Kali? There it is. Oh, good. It's logged me out. I'm going to close this one. Close without saving. Open Cutter again. Open reverse 1. Open it. We'll use the default settings. Analyzing the program, loads it up. We're familiar with this. We know that we can go to main, and we get the main function in our program. So I will give you, let's say, 4 minutes on this. You have 4 minutes to try to figure out what's going on inside this program. And before we do that, let's run the program just to see what it does. I can hear Josh screaming from here because last year I told people that when you get a binary, the first thing you should do is run the binary. Don't. That's only for if you're doing a CTF. Let's assume that in a CTF, they're not giving you malicious programs, although I think we did one where that might not have been the case. When I'm giving you programs, none of them are going to be malicious. You can run them without worry. So let's run reverse 1. Reverse 1 prints out 13. Let's run it a few times. Yeah, it's always going to print out 13. Yeah, Josh will tell you don't always run strange programs, and that's good advice. You can run this one. This one's printing out 13. The question is, what's it doing that it's printing out 13? So we're going to go to Cutter. We're going to take a look, and things are going on in here, but we're not quite sure. We've got main. It's declaring a bunch of things. These are variables again. Some of them are ints. One of these seems to be some sort of char. And then it's moving down, and you should notice in green, at least on my screen it's green, there are some jump statements. So let's see if you can figure out what it's doing that the number 13 is being printed out. I'll give you guys 4 minutes to try a quick trace of this and see if you can find out what it's doing. While you're doing that, I'm going to go grab some water. 2 more minutes. Answers are starting to come in. Okay, let's call it there. We've got 2 people that got it. Rad McDad, it's a loop that adds 1 to 3 10 times, and Racina, could pronounce that right. Yeah, it's a loop, and it counts up 10 times and adds 1 to the value. So we're going to take a look. There's a lot of stuff going on in here at the beginning. Remember, I said you can kind of ignore. I said you can ignore the first 3 lines of the last one. This one, you're going to ignore quite a few of the lines up here. The interesting stuff starts happening down here. So it puts 0 into var ch, it puts 3 into var 10. It then jumps. Remember, that's just an unconditional jump. It's just going to jump. Cutter, thankfully, gives us some arrows. It tells us where it jumps to. There's no label here. This is the memory address that it's going to jump to. These addresses down the side, that's what that's telling us. So it's jumping down here. First thing it's doing is comparing 9 with var ch. That's going to be 0. So it compares 0 and 9, and then it jumps if less than or equal to. 0 is less than or equal to 9, so it's going to follow this arrow up. It's going to add 1 to var ch, which was 3, so now it becomes 4. It's going to add 1 to var ch, which is now 1, and then it does the comparison again, so now it's 1 and 9. So this is just going to loop until var ch reaches 10, at which point 10 is not less than or equal to, and it's going to keep running the program. And then we see down here it calls print. It sets up the values to be printed again. So yeah, that's what this program does, is it just runs a loop and prints out the answer. This is what the C program looks like that you were just reversing. There's int I. This is going to be the loop counter for the for loop. Answer is 3. Runs the for loop 10 times and adds 1 to the answer each time and then prints it out. That's all it is. Not a complicated one. Really straightforward. Good. So you've now reversed your second program. That was reverse 1. So why are we doing this, or why is this a popular thing? Why is it important? To relate it back to something that you might be familiar with, back in the day when you bought a program, it usually used to come on a CD or, if you're much older, a floppy disk. But if you're Jeremy and you're 11 years old and Christmas is good to your neighbor gets Battlefield 1942 for Christmas. And that's great because now they have the Battlefield 1942 CD. And they can install Battlefield 1942. And the problem is that in order to make sure that they're just not copying the CD and giving it to Jeremy, the CD has a key on the back of it. Some people probably remember this. This is how you used to ensure that people weren't just copying the programs and giving them out to all their friends. But Jeremy's neighbor did copy the Battlefield CD and gave it to Jeremy. But how is Jeremy going to install it without the key that his friend Mike has? There used to be, if you're familiar, and this slide isn't set up quite properly, there used to be these programs. Let me just fix this. You can front and animate, restart. Yeah, it is any program used to ask you for your product key. It was located on the CD case. You had to put it in. If your neighbor had copied it for you and didn't give you the product key, then you were SOL. You had to try to install it, and maybe you could guess this, but you usually couldn't. There was something to it, and you didn't know what it was. CDs used to have these product keys on it. There's Windows 10 with a product key. It's crazy to me that people would still buy Windows with a product key. If you use Steam and you game, you might have seen this window. You can redeem your old product keys on Steam to get access to it through Steam. The way that you used to be able to get product keys is with these keygen programs. You used to go to these websites that were sketchy AF. They used to look something like this. They would have long lists of programs in them. You would search for your program and see if they had a keygen for it. They would kind of look like this. They were really sketchy, and they just had all of these programs in them that would generate keys. You used to find them, they would say, activate any software for free. There's no program that could do that. It would have to know exactly what kind of key or what specific key the program needed. Anything that told you it could activate any software for free was very likely not a good program. It's not something you should be downloading. There's other ones. They looked like this. You knew it was really legit if it looked like this. Any kind of skull and crossbones or dark background was the sign that some elite hacker had built this keygen program. It came off of a website that usually looked like this. So someone had set this up in 20 minutes to lure unsuspecting 12-year-olds into downloading programs to run on their computers, probably. It had all kinds of keygens. If you downloaded the program and it looked like this is probably not one that you wanted. Sometimes it was in a different language. That was usually a sign that you shouldn't have downloaded this and something bad is probably happening. What you would do is you would close the program right away, and that would stop everything, of course, and your computer would be fine. But 12-year-old Jeremy wanted to play Battlefield 1942 and didn't have the CD key because his neighbor didn't give it to him. But that's okay, because being 12 years old, Jeremy might not be very clever, but Jeremy's wicked smart. And Jeremy knows that he can download the keygen program off some sketchy internet site for Battlefield 1942, and he can generate a key. And this is great because now he can play the game. The question is, how did the keygen program get made, and who made it? Well, what was going on was that people were taking the CD, taking the program, reverse engineering what was on it, figuring out how the keygens the keys were being generated, and then building a program that would generate keys that worked. So on here was this little program that was looking for specific keys. Maybe there was something about it, usually something cryptographic, but if they were being broken, they weren't very secure, obviously. You would download this, you would get a key, you would run the program. So reversing was really popular in the late 90s and early 2000s for doing this kind of stuff, breaking programs that had these copy protections on them. That's something that you might recognize reverse engineering for. Today, it's used a lot. You hear about it with malware and viruses. You get a virus on your computer. There are people who run computers that are trying to get viruses. They take those viruses and they reverse engineer them to see what the virus is doing and break it down to see what's going on inside the program. So in Cutter, we're going to look at we're going to look at the next program. The next program is reverse 2, I believe. It's my Kali always disappearing. There it is. Yeah, the next program should be reverse 2. So reverse 2 is paying homage to the history of reverse engineering. Reverse 2 wants a command line argument. So let's give it a command line argument. Let's call it argument. Program says you entered product key argument and then tells us the product key is wrong. We need to know what is the argument that's going to get us into this program. What is it we need to type in? Things? Is it stuff? It doesn't like that at all because I've written too much. Nope, too many exclamation points. It's interpreting it wrong. You can write multiple things in here in quotation marks. So multiple words. Multiple words is not it. Question is, what's the password? What's the product key that's going to get us into reverse 2? I'm going to give you about 2 minutes to see if you can figure it out. Yeah, I missed out on the chat. Here we go. Product Photoshop, Pirate Photoshop. I wouldn't know anything about that. Yeah, download the Bonsai Buddy keygen. Awful stuff. So take a look at reverse 2. Remember that list of things that we did on the first program, reverse 0? Try to think of what we did there and see if we can find what the key is that's going to let us in there. Also, if anyone gets it, just pop in the chat that you found the password. We've looked at a few different tools that we could use. All right, so a few people are getting it. I'll give you 30 more seconds. few different things you can do to get into this one. I'm not actually sure how many people are watching this right now. I'm sure there's only about 6 or 7 people that are vocal in the chat, and then thousands and thousands are just silently working in the background. Okay, let's take a look at this program. So if you followed what we've been doing so far, you've probably opened it up in Cutter. So let's close without saving, and let's open reverse2 in Cutter. Actually, no, before we do that, on the list of things that we did with our first program, we ran it was the first thing that we did, and the second thing that we did was to run strings on it. So let's start with that. Go down the list. It's always good to run strings on one of these when you're trying to figure out what's inside of it. If we look through, we can see some things that are familiar over here. Requires command line argument, multiple words in quotes. We saw that earlier. That was what happens if we don't put in the command line argument properly. We saw wrong, access granted. That's probably the message that it gives us when we get it right. This is interesting. What's this? Time rich and cache poor, and you entered product key. Well, there's some possibilities. I have no idea what these are, but that is a good candidate. And so when we try it out, which I'm guessing a lot of you did, you would have found that access was granted into the program. Why was the product key being hidden inside the file? If you opened it up in Cutter, you would have seen the following. Reverse2, open. Loading it up, we go again to our main function, and there's a whole bunch of stuff going on here. Cutter, at least in my version, this didn't happen for some of the people last year when we did this. The settings that are set up on mine, it's telling me what the strings are that it's loading to run comparisons on. You entered product key, time rich and cache poor, access granted, wrong, and then requires command line argument. From how we've run from running the program ourselves, we know that requires command line argument is something that happens when we don't put the right arguments in the command line. And if we check over here, there's a big arrow that comes from the beginning of the program and jumps down there. And down here is almost the end of the program. I forgot to mention earlier, this instruction down here, RET, stands for return. This is where the function ends. So main will start up here underneath this heading. This is the first instruction. It'll finish when it comes to the RET instruction down here. So this program, it's checking something, and then it jumps way down to almost the end of the program if a check fails. What it's checking is that you've put in a command line argument. If you haven't, then it jumps down here and tells you to put it in and gets out. Otherwise, it's loading some strings in. One of them is you entered product key. So we know that that prints out whenever we enter a product key. It then loads this string in, time rich and cache poor, loads it into RSI. This LIA instruction is telling it to load something into this register. It's loading whatever is at this address. Let's just take a look, 2025. The address 2025 is being loaded into RSI. If I go to strings, time rich and cache poor, this string is being stored at 2025. In fact, if I double click on that here, it'll jump to it. So in the program, the string is being stored in the program as a line. That's why we can read it with strings, and that's why it's finding it. So it's loading that in, and then I am betting it runs something called string compare, strcmp. That's one of the functions it's going to import. String compare is going to compare what we entered and time rich and cache poor. It then does a test, and then it does a jump. Where does that jump go? It goes down here. It goes to wrong if they're not equal. So if the product key and what we entered aren't equal, we go down here, it prints out wrong. Otherwise, it skips this, prints out access granted. Yep, and then just jumps over the wrong statement. So that's what the control flow is looking like in our product key program. If you opened it up in Cutter, it was nice. Sorry, I've jumped around. It was nice. It just told us what the string was that it's putting in there. Reverse engineering is nice because you can sometimes just find these things in there. If somebody has been lazy with their program, maybe they just wrote the password that it's looking for inside. So you're saying that sorry, I forgot to answer this question from Steam Blizzard. So you're saying that old disks used to have their game keys actually in the disks. Not on the disk. Like it wasn't inside. It wasn't inside the program. The key that you had to enter was actually on the back of the case usually, or on the instruction manual that was inside the box. But on this disk or inside the Battlefield program, there was a little program inside that checked whatever the key was that was entered to make sure that it was a good key. So maybe the key was looking for like every second digit had to be even or odd. That's a little simple, but it would do things like that. You could type some stuff in and it wouldn't work, but some keys did. So there was something going on underneath that it was doing to check if the key was good or not. These programs were going onto the disk, figuring out what it was looking for, and then writing a program that would generate things that passed all of the checks for the key. So these key gens would just generate keys that always worked and unlocked the disk, unlocked the program to run. Otherwise, the program would be locked. This just doesn't happen anymore because everyone's connected to the internet all the time. Your program just checks against some server saying, am I legitimate and can I be run? When you buy a game on Steam, I believe you get one of these keys. Steam checks to make sure that the program that you have that you're running is legitimate and that you actually bought it. I'm not going to try to do it because it's going to take too long. But I could go into Steam and I could probably find the product keys for all the games that I have. I think it gives them to you still in case you want to run the game offline, which I think is something that it's supposed to allow you to do. It just makes it really hard for you to do because if you do that, then you can start trying to do this stuff again. You can start trying to copy games. Yeah. So, let's look at control graphs. This is not something we've looked at yet, but in Cutter, there is this thing called a control graph. I'm not in Cali. Here we are. Down at the bottom, again, there's more tabs. One of them says graph. This, we can pull and move around. This is showing us the control flow of the program. So like back at this disassembly, all of these lines that are saying like jump here if this happens, jump here if this happens. This is what it looks like as a nice graph. So it's going to run this part of the program. And then we see the jump statement, and there's two lines, green if the jump is true, red if the jump is false. So it does this. If the jump is true, it goes over here. This was that big jump that we saw. That jumps from like the top almost to the bottom of the program. That tells us that we didn't put the right number of arguments in. If the jump fails, which might seem counterintuitive to you, we want the jump to fail. We want it to load to check the product key. So this is where it was loading our argument, our product key. This is where it was loading the string, the product key that we were trying to check, time rich and cache poor. Then did another comparison. It would go wrong if that comparison was true. It would go access granted if the comparison was false. So we can use this, and then all of these then go down here, which goes to the RET. This is what ends the program. So you can look at this in Cutter and try to say, like, where is it that I want to go? I want access granted. Okay, to get access granted, I need this to be false. Okay, so then I need this to be false, which means, and you can start back tracing it through the program and seeing what it is you need to put in to pass each of these steps. So you can start crafting what it looks like. Other things down here, I should say, there's also the hex dump. This is showing you when we ran XXD earlier on, Cutter has a hex dump built in for you. This is pretty. This shows us what all those bytes are, and then it translates it over here. You can see the reason that we can read this is because that product key is just written into the program. So when it was compiled, it put it into the computer, or sorry, into the program's data. So we can highlight it here, and it'll show us over here. It'll actually highlight the bytes that contain that product key. And then here are the other ASCII parts that were inside of it. So this is nice. We don't have to run hex dump. This is also prettier. It shows us things. I think you might be able to search through this. And then let me just make sure. Yes, we used strings. We used XXD. Oh, a little homage. Does anyone know who this guy is? Anyone? You call yourself nerds. No? All right. This is the guy from which the product key, our quote, time rich and cash poor, is a quote from a guy named Cory Doctorow. The quote is, "Never underestimate the determination of a kid who is time rich and cash poor." And this line was taken and applied to all of the people that were just sitting at home wanting to play games that were protected by these product keys. And so what they were doing was reverse engineering the programs, learning how they worked, and generating, building key generators. Cory Doctorow famously fights for like electronic rights, so rights on the internet. He was awarded a prize by the Electronic Frontier Foundation. He was a blogger. He was big in like nerd culture, and when blogs were early on, he was very popular. So popular that he became a character in XKCD. This is him showing up wearing a cape and goggles. The joke was that he lived in a balloon and blogged from there and fought for people's rights. Cory Doctorow embraced this, and when he was given the award by the Electronic Frontier Foundation, he showed up in a cape and goggles with a balloon. So he's the one that the quote comes from. So yeah, reverse engineering is something that was done by kids who were time rich and cash poor and wanted to play programs. Good Cory Doctorow. The next thing I'm going to show you, the last tab over here. Some of you might have already gone over. It's not showing us anything. I need to tell it where we want to go. We want to go to main. So this is the decompiler. What the decompiler is doing is trying to turn our binary back into C. And if you look, this is what it guesses the program looks like. So you might remember our picture over here. We started out with the executable file, just the zeros and ones. Cutter was turning it back into assembly code for us, and we were reading that. But Cutter also then tries to turn it back into C, into the source code. Those two tabs at the bottom were disassembly and decompile. Basically reverse disassembly, so reverse into assembly, and reverse it, decompile it is like take it backwards through the compiler back to the source code. Let's take a look at that. Remember I said our goal was to get it back to C so we could read it? Like if we needed to look at this would have been much easier. I said that this is very difficult, and this looks very easy to read for us, and that's because when I compiled this program, I told it to put in a lot of stuff that made this easy. Normally when programs are compiled, all of these strings in here are chopped up and obfuscated so that it's not easy to turn it back into C. I made it so that this was easy. You're going to see that, I double clicked on something. You're going to see that this isn't always true. There's another program I've written that doesn't make it very easy. So yeah, this is what the decompiled version looks like. This is what we would like, is to turn it back into C, but it's very difficult. And I'll show you why. We're going to go back to that. Let's go back to that picture. When the C code is compiled, it goes through this thing, the compiler. The compiler makes a bunch of decisions about your program, and it optimizes it. Something called optimization, which is basically it decides how to take your code and turn it into assembly in a way that it is programmed to. It's programmed to think will make the program run faster. I'm going to show you a program soon with different levels of optimization inside of it. And you're going to see that with one program, the compiler can change it in different ways. So the reason that turning the assembly back into the C is difficult is because sometimes the compiler makes weird decisions about how it translates it this way from C to assembly, so that when it tries to go back, things don't necessarily make sense because the compiler has done things to improve upon your code. Yeah, let's go back to our presentation. This is the program that we just ran in GDB. So we're going to go back to GDB, and I'm going to demo to you some of something that GDB can be used for. Where's Callie? Right here. Go back, clear this. We want reverse 2 in GDB. So I'm going to do that. GDB is now waiting for what we want to do. So I'm going to tell it to disassemble main. I want to see what's going on in main. Something you're going to notice right away, if you're paying attention, is that this doesn't look like the assembly that we were looking at in Cutter. This is main, percentage RBP, percentage RAX. Let's go back to Cutter. Cutter didn't look like this when we had the disassembly. Back to main. Push RBP. It doesn't have those percent signs. What's happening is, sorry, I keep switching out of it. What's happening is there are different what are called flavors of assembly. Do I remember how to do this? Set flavor? Intel? Oh no, I've forgotten how to do it. I should be able to switch this back to Intel assembly. I just didn't write it down. And I can't remember what it is. This is when Google is our friend. GDB. I can see set flavor Intel is part of my search history. Set disassembly flavor. That's what I want. There. So now when I disassemble main, it's going to look different. Yeah. Now we don't have all those percentage signs. Basically, same language, just different way of looking at it. The other one was called ATT. This is Intel. I think the split is usually among Linux and Windows users. One of them uses ATT more. The other one uses Intel. GDB will just translate it between them. So what we want to do in here is we want to take a look at what's going on with all the values in the program. We can see the string compare happens here in the program. So we could tell the program to break here and, break right after, because that's the string compare. So it's comparing our product key and what we guessed the key was. Then it's running the test, and this is the jump statement. We need to figure out what's the value, what is it we want from string compare to make our key and our guess equal. So let's go and see if we can figure out what it is that string compare does. I'm going to open another terminal window here. Man strcmp. strncmp. String compare. strcmp. Okay. For some reason, it doesn't want to show me the manual for this. If anyone sees what I did wrong there, let me know. We're going to search it online. strcmp, string compare. So this is, you should be able to do this in here, and it should give us the Linux manual for string compare. I just reinstalled Kali, so I've obviously missed something that I didn't install something. So it tells us about string compare. String compare takes 2 arguments, 2 character constants. So these are 2 strings. It compares the 2 strings and it returns an integer less than, equal to, or greater than 0 if it's found to be less than, to a match, or greater than. The return value is an integer less than, equal to, or greater than 0. Basically what it's doing is it's comparing the 2 strings. It's comparing the values of each character. If the characters aren't the same, then the values are going to be different. And what it returns is the difference in all of the values. If the strings are the same, then the difference is always going to be 0, and it returns 0. So if the 2 strings are the same, string compare returns 0. That's what we need to know. I'm going to go in here, and I want to set a break. I'm going to run the program first. So it tells us it run. It wants the command line. It exits normally. I'm going to disassemble main again because I need the virtual addresses to be set. This is our string compare, and then this is the test. This is where it's comparing the 2 things. I want to break the program right here. So I'm going to copy that memory address. I'm going to say break star, and then paste the address. It's not going to do it for me. OX 0000555555555183. Bet you dollars to dimes I didn't put enough 5s in there. So we're going to run it. We can put our argument in here. You've been hacked. So we've reached the breakpoint. Apparently I did it right, I think. So the program has stopped right here in the assembly. And let's see what the values are. So it's testing EAX. So I can type info registers, and this is going to tell me what each register in the program is set to. So all those registers I showed you before, GDB is showing us what they all are for this program right now. It was comparing EAX, which is the lower version of RAX, the half the size of RAX. So this is the register where it's keeping it. There, that number is huge. We want that number to be 0, and it's not right now. If we run the program, if I tell the program C to continue running, it's going to tell us wrong. Our guess was wrong. Let's try running it again with the same string. It reached our breakpoint again. I go info registers. Yeah, still same thing. We want that to be 0. I think I can do. So what I'm going to do is I'm just going to set it to 0. I'm going to tell the program, instead of the value that you have there, make it 0. So now when I go info registers, yeah, now it's 0. So remember, this is the spot where the program was returning the string comparison. If the string comparison is 0, then the strings are the same. You know that I entered you have been hacked instead of time rich and cache poor. So if I continue this program now with that value being 0, it'll do the test. It'll say, oh yeah, string compare says that these are the same strings. And there we go. Access granted. So this time, because I had changed the value that string compare was returning manually, it went the other way in the program. The control flow changed. So GDB is really useful because it allows us to do things like that. That's a little trick that will be useful. Yeah, this is that program. So we had the string compare here, and this is where we did the break, and we changed so that the jump went differently. Before it would have jumped to wrong. This time we changed it to 0 so that the jump went to access granted. Yeah, so remember, we've learned about going from source code to executable. The middle step of assembly, we've learned about going from executable back to assembly, and then even how to get from assembly back to the source code. I'm going to show you, I told you that sometimes the compiler makes decisions about how it translates it into assembly. I'm going to show you that now. Here's the reverse 0 program that we went through at the very beginning, the one that adds 2 and 3. This is it, but it's optimized at 3 different levels. So optimization level 0, basically the compiler is not making decisions about how to run the program faster. So when it translates it this way, this is the one that we saw. It takes 2, it takes 3, it adds them together, and then it moves them around, and then it prints them out. When I optimized level 1, you can see here that instead of taking 2 and 3, it just moves 5, and then it immediately prints. This is the same program. It does the same thing. It's the same C file, but the compiler, when it translated it into assembly, made a decision that this program can run much faster than you've written it. When you take A and you make it 2, and you take B and you make it 3, all you're doing is adding those, and then you never use them again. So the compiler just said, instead of doing all that stuff with 2 and 3, let's just use 5, because that's all the value is in the end. And then it prints it right away. So it's far shorter. And then optimization level 2 is basically the same thing. I think the only difference is this move instruction here, 0 to EAX. This one just XORs it, which, if you remember how XOR works, anything XORed with itself it is just 0. So this one moves 0, this one just XORs. Because whatever it was that the compiler was told to do for this level of optimization said that this is the way you should do it. At this level, it said it was this way. And I can show you kind of what that looks like. Let's quit GDB. I have a file called compiles. Yeah, so here are those different, this is the reverse 0 program. I've compiled it 4 different times with different levels of optimization. When you compile a C program, we use GCC. This is the compiler. I'm then manually setting the optimization. So I go O, capital O, and then 0. So this is optimization level 0. And then I want reverse 0.c. That's the C program. And then reverse 0. So it's telling it, compile this program, reverse 0c, with optimization level 0. Sorry. And then put it in reverse 0. And so it runs it. What's it upset about? Oh, there is no, sorry. I need to change this to tell it to create the file if it doesn't exist. Bam. So that's what compiling looks like. And this thing that compiles, that translates it from C into the binary, it's translating it into assembly and then into the binary. And when it translates it into assembly, it makes decisions about how it thinks the program can run faster when it translates it. And that's why it looks different over here. And this is one of the reasons why translating things back from the binary back into the original source code can be difficult. Because if you look at this program looks like it's just printing out the number 5. We know that it was actually adding 2 and 3, but the compiler decided that it's just faster to print 5 instead of adding 2 and 3 together. If we tried to reverse this, it would tell us that the C code is probably just take 5 and print it. In fact, I think if you open it in Cutter, that's exactly what it tells you. So we're almost finished. Let's open this in Cutter. I'm going to open one of the let's do 2. This is one of the optimized programs. So we have the disassembly. Go to main. See that it just takes 5 and it prints out 5. And then when I decompile it, yeah, it says the program is just printing the number 5. We know that that's not what the original program looked like. We know that it was actually taking 2 and 3 and adding them together. So this is one of the reasons that things get complicated when we're reversing from binaries. So yeah, now there's some challenges for you guys to do. There is a file that you should all have called reverse challenge. This one has a flag. The flag is worth a whopping 75 points. It's a big one. I'll tell you that it's more challenging than the ones that we've done so far. It's not as straightforward. There are multiple ways to get the flag out of this. Everything that we've done, almost everything that we've done in this workshop so far, has taught you a different way to get the flag out of this file. There are some very easy ways. There are some much harder ways. When I had you download the programs or download these files, there was a Mac file for people that were on Macs and a Linux and Windows file for people that were on Windows and Linux. I think you should be able to run this program if you downloaded it for the right system. Hopefully that's the way that it worked. Let's see. We're going to run reverse challenge. I promise you this is not... oh yeah, I'm in the wrong place. chmod 0777 reverse challenge. Yes, it wants to know what the password is. The password is Tings. And it tells us that's not the password. If you get the password correct, it will print out the flag for you. So remember, like I said, flags are kept inside the files. Somewhere in this file is the flag. There's also a password, except this time I have done some things to obfuscate it. I will tell you, I have chopped it up into pieces so that if you try to strings the file, it's not going to show up. I've also cut it up into pieces all over the place, and then it does some stuff to create the flag and the password again. So yeah, you can go at it and see if you can figure it out. Give it to Orchid, and there's 75 points in it for you. If I go into Orchid, if we check out the leaderboard, yeah, top place on the leaderboard is 500 points right now. So 75 points is like quite a few. To get on the top 10, you need 314. So 75 will get you like a third of the way to getting onto the leaderboard if you can figure out this challenge. I've also included in there another thing called lolcode.lol. So reverse engineering, we've gone through like the basics of turning a binary back into a program and trying to figure out what the binary does. Reverse engineering is also just trying to figure out what any program does. It doesn't necessarily have to be C. We've done it with C because that's what a lot of, or that's what I'd say the main way of doing it is. If you're trying to figure out what actual programs do, lolcode, the program, is written in something called an esolang. And let me pull the website up for esolang. So esolangs are esoteric programming languages. Esoteric meaning obscure or not popular. So these are basically joke or project languages that people have come up with. You know Python, Java, C, you know all of those. People will sit out there and spend their spare time coming up with these languages. What are some interesting ones that we've done? Emoji gramming esolang, I think, was one of them. Yeah, so Alex, Emily, and I did a challenge at a CTF that was written in this. This is a programming language. It's just emojis. These all work like assembly code. They tell you to move, print, add, subtract, jump. They all have special meanings. They tell you what they are up here. It looks pretty simple, but it's pretty complicated. We did a reverse engineering challenge where we were given this and had to figure out what the password was to get the flag, or to get the flag out of it. So that's reverse engineering. What you've been given is something called lol code. So lol code is very similar to C. This explains how lol code works. Essentially, you're going to learn, if you want to trace this challenge, you need to learn how this language works and figure out what it's doing. I have never run the language, so it might not be 100%, but I did sit down and figure out how it works. It's pretty jokey and memey. Let's see, do I have it opened? I do. This is what it looks like. Learning new languages is part of reverse engineering. You've got to figure out how things work. So this is lol code. This is a challenge that you could find in a CTF. I've built it for the end of this workshop. All of this does something. All of this is moving stuff around. Look, there's a use csec right there. That's useful. So there's a flag hidden somewhere in that program. Try to find it if you've got some time. I know it's midterms and everyone's just got tons of time right now. Yeah, Arnold C is... Let's see if we can find it. Arnold C is another one. I wonder if it's listed in SO langs. Also, before we switch, lol code is Turing complete. They know this because they built an interpreter out of this language that interpreted another SO lang called, and vulgarity incoming, brainfuck. It's a famous language that's written that makes absolutely no sense and is difficult to read. But somebody built an interpreter out of lol code for that language, which is absolutely crazy. Arnold C. Yeah, this is, I think this is all built out of Arnold Schwarzenegger quotes. Yeah. I need your clothes and your boots and your motorcycle is method arguments. Stick around is for while. No problemo is true. Yeah, these are what SO langs are. So this is also some fun thing that exists out there. Yeah, so the rest of it, you can work on lol code, the reverse challenge. Pico 2018 has some good reversing challenges that I'd recommend, good starter ones, and you can use everything that you've done here to learn those. So yeah, that's going to be the workshop for tonight. You guys have learned the basics of reverse engineering. You can go out and use that for good or for evil, but remember, try to use it for good. Yeah, I hope this was helpful. If anyone has any questions, by all means, just toss them in the chat right now. I can stick around for a few minutes. But otherwise, yeah, that's the end of the workshop. I hope you signed the attendance form if you were here. Let me just double check. I believe next week is... Oh, I don't believe next week is reading week. It is reading week. So next week is reading week. There's no workshop next week. And the week after that, the intro workshop is going to be SQL code injection with James. The advanced workshop in 2 weeks is going to be Docker and its exploitation with Alex. After that, we have our next speaker, Kathy McDonald, speaking about cybercrime. Kathy is a retired police officer. She spent 25 years with the Calgary Police. She's a senator at the University of Calgary. It means that she's one of the people that kind of helps run the university. She's very accomplished. She focuses now in cybercrime. She's written a book about it. She's really interesting. I hope you consider coming out for that. That's going to be on the 23rd of November. After that, there's one last workshop, binary exploitation, or RSA, which is a cryptography workshop with Braden for the advanced. But I'll be doing binary exploitation. That one will go more into this kind of stuff. We're going to look at how to break programs that haven't been programmed safely. So basically how to get a program that's not programmed right, how to break it and take control of a computer using this. It's the basics of, it uses something called a buffer overflow, which is one of the basic ways that computers get broken into. It's very, very common way to hack machines is to find buffer overflows in programs and use them to take control of the machine. We're going to go over the basics of how it works and then run some buffer overflows so that you'll know how that works by the end of that workshop. And yeah, that'll prep you for next semester when we have a few more workshops that deal with binary exploit. Yeah, so that's it for tonight, everyone. Thanks for coming out. Let me just make sure that there weren't any questions. Yeah, someone just needed the link. Okay, otherwise, everyone have a good night. Thanks for coming out. We hope to see you in 2 weeks. Remember, the next speaker is coming up. Any questions, go into the Discord. Remember that there's also been a playlist that's been shared in our Discord. People have been adding music to study with. I found some stuff that I like in there. Some of it I skip, but yeah, feel free to add 5 songs in there and listen through to help you study for what has been a grueling midterm season, I'm sure. So yeah. Otherwise, signing off. Thanks everyone for coming out. Have a great night. Stay happy, healthy, and unfortunately quarantined. We'll see you in 2 weeks. Have a great reading week and have a great night, guys.